class. Okay, so we're going to move on to a slightly better model, what's going on inside a metal. This is the Drude model, which is, of course, pre-quantum, so it's not exact. But it's based on a couple assumptions. So first off, we assume that the electrons inside the metal are free to move around, and they move around in the absence of an external electric field. They move around completely randomly. So, some are going to the left, some are going right, they can be going up or down. So 3 dimensions. They have a completely random velocity. And they interact, though, with the atoms that make up the metal. Like, say, this is copper. So you have these electrons moving around. You have these atoms. And the electrons can collide with the atoms. Not a great picture, but get the idea. So that's one assumption. Now, these electrons that move around randomly, this is actually called an electron gas, which it's not like the gases we've encountered before, which are based on like this Maxwell-Boltzmann distribution. These work a little differently. Typically, the actual speed, the average velocity of an electron in a conductor is somewhere around 10 to the 6 meters per second. So again, they move around extremely rapidly, but totally randomly. So if there's no electric field, there is no current in this wire. So even though there's a lot of charges moving around, due to the enormous number of charges, and one per atom that are free to move around, and I forgot we kind of did that calculation in the last problem. We had like 10 to the 22nd power atoms per cubic centimeter, close to 10 to the 23rd power. So with a huge number, so these averages are very valid in this case. And you have just as many moving to the left as to the right, or like in any direction, you have just as many going one way as the other way. So there's no net charge. So if we draw our surface here, there's a huge number crossing from left to right, but an equally huge number crossing from right to left. And they, equal numbers, they totally cancel each other out. So there's no current here, unless we apply an electric field. So let's say we apply an electric field in this direction. Now, how would we actually apply this electric field? We would set up a potential difference between the ends. So our electric fields go from high potential to low potential. Let's set the right end to 0. The left end is just at a potential V. And what is the effect on these electrons? Well, there's a force acting on them. And the force will be to the left. So like the force on any given electron, let's just say this one here, that'd be the electric force. That's to the left because it's a negative charge. So the force is in the opposite direction as the electric field. And so there's going to be a net tendency for the electrons to move to the left. Now, we're going to see that like if you had, say, this electron, its path was looking like this. This is a path with no electric field. Now, the actual effect of that electric field is going to be very small. Like the actual path, and we couldn't even draw it on a proper scale, but it's going to cause the electron to drift a little bit leftward from where it would have gone. So this was with no field, but it's going to have a force pushing it to the left. And again, something moving to the right would, instead of taking this path, it's going to be drifting to the left a little bit. So like this is the actual path that it would take. So let's call this V. Say that's V prime. So like V is what you get without the electric field. V prime is what you get with the electric field. But again, these pictures are enormously exaggerated. The actual change in velocity is going to be extremely small in practice. And it's going to continue moving until it hits an atom. And that collision is going to randomize the motion. So again, this is the Drude model. Once it hits an atom, it's going to bounce off with a random velocity in a random direction. Now, one thing we can say about this is that the electric field is doing work on these charges. It's applying a force through a distance. And so that would, there's energy being supplied to the electrons. However, they're not really gaining energy because of these collisions. So when the electron hits the atom, it's giving that extra energy it got from the electric field to the atoms that make up the conductor. And you can see the result of that. You can even see it visually sometimes. Like if you have a strong battery and you just connect a wire from one terminal to the other, if you wait long enough, you might even see smoke coming out. The effect, though, is heat. So these collisions are turning that kinetic energy of the electrons. So they're constantly speeding up or changing their velocity anyway because of the electric field. But that extra energy is just going into heat from the collisions. So we're basically assuming that we have an electron gas where the motion in the absence of an electric field is totally random. And the collisions completely randomize the motion again. So it's going to hit an atom, and then the velocity afterwards is going to be random. So let's look at one electron. So let's say our electron was doing this before, and then it's going to hit an atom and bounce off. Now it's going to, and then of course it's going to hit another atom, and then another one. And we're going to define tau, this Greek letter tau, to be the average time between collisions. And again, it's going to be different because its velocity and the direction it's moving is going to be randomized with each collision. Okay, so in between from, when it hits one to hits the next, we know that the force on this electron is constant. The force is just QE. Let's just look at the magnitude. It's also the same. We have an electric field that points in one direction. So we could put arrows above this, but let's just look at the magnitude. So we have a constant force, which means a constant acceleration, ma. And so the acceleration is QE over M. Or, because we're talking about electrons, the charge is the elementary charge E. M would be the mass of an electron, which is of course rather small. And let's look at, let's look at one electron as it goes from like one atom to the next. So it hits one atom, we'll say at t equals 0, and then it's going to hit the next one at some later time. I don't want to call it tau, because tau is going to be the average for like every electron over some period of time. And what happens, remember, just from constant kinematics, constant acceleration kinematics, let's just look in the x direction. The change in velocity in the x direction is going to be equal to the acceleration in the x direction times t. And again, the acceleration is purely in the x direction because that's where our electric field is directed. And so this delta V is A times t. And now you might think, yeah, we're going to take an average value. Let's do that. Let's average this over all of the electrons in our gas, like our electron gas. So we take an average over everything. And what I'm going to say is that this average is what we call the drift velocity. And that's A times tau, the average time between collisions. Now, this might seem wrong at first, because if you look at an atom, it starts out with a velocity v prime at t equals 0 when it leaves this, this atom here, and then at some time later, an average time of tau, it's going to be moving with a velocity v prime. So delta v, the final velocity, will be just a times t greater than the initial velocity. So it's accelerating the whole way, and this a times t, that's like the final velocity, or the final change in velocity between starting and ending. So we might think there should be a 1/2 here. But that's not the case because we have to look at the entire gas. So let's just say at one moment in time, we take this average delta V, and the change in velocity for each electron is its acceleration, which is the same for each electron, times tau, which is the time since its last collision with an atom. And so, it's kind of a real subtle point, but we don't have this factor of 1/2 in front. If we considered a single electron, then delta V, like the average velocity would be 1/2, or the average change in velocity would be 1/2 times A times tau. But when we take the overall average, that 1/2 does not appear. The drift velocity, we consider that kind of like the average velocity, or the average change in velocity due to this electric field. Again, the way tau is defined, we don't have that factor of 1/2. So this is the time since their most recent collision. We set t equals 0 there. And so the drift velocity is just A times tau. Now, our acceleration is the elementary charge times the electric field over m. So, we plug that in, we have our acceleration times tau. Okay, so that's the result we get from the Drude model. Kind of a real subtle argument here, but otherwise a pretty simple result. Now, again, this was not based on any particular model, really. Actually, we were looking at that particular model where we considered every particle to have the same velocity, but now with this more advanced model, we call this drift velocity, which is defined in this particular way. So it's like the average change in velocity between collisions. So tau is the time between the collision of one electron from like when it hits one atom to the next one. So let's look at the current density. So the current density, we have N. I'm going to write E instead of Q. Q is a more general result because a current can have any charge. You could have an ion with, say, a doubly ionized atom or molecule, where Q would be 2e, or it could be negative 2e, whatever. These are just magnitudes, so don't worry about the signs. But yeah, in this case, we're looking at electrons. So we have NE times the drift velocity, which is the little e big E over m times tau. And going to write this way. Okay. Now this Drude model applies somewhat accurately to the the electrons in a conducting metal. Doesn't apply to every type of material possible. We're just looking at metals right now. And if we look at N, remember that's the number density of charged particles that are free to move around. And so for a particular metal, that's constant. E is a constant, of course. M is the mass of an electron. Now, tau is also going to be constant. That might seem surprising because you think if you have a stronger electric field, the particles are going to be moving faster, but that's not really the case. The time between collisions will not be affected. Remember, the velocity of these particles is around 10 to the 6 meters per second, where the drift velocity is actually comparable to what we did in our more primitive model, like 10 to the minus 4th or 10 to the minus 5th meters per second. So the drift velocity, that's a result of that electric field. That has a very tiny effect on the overall velocity of these electrons. And yeah, so tau is a constant as well for any given metal. It would be different for different metals. The spacing between the atoms could be different, for instance. And so basically for any given metal, everything that I wrote here is constant. And so we define sigma to be N E squared tau over M. So we define sigma this way, and we get this result for a metal. Then J is equal to sigma times E. This has a name. This is called Ohm's law. And again,